Hi, in this video I'll talk about sorting algorithms. What are sorting algorithms, you might ask? They're used for searching through and sorting large amounts of data in databases. They have become uh, they have become increasingly more important as the amount of data has rapidly increased since computers first um, began. Also, knowing these algorithms is important because they're frequently asked on interviews. So in this video, I will go over the four most common sorting algorithms. The first sorting algorithm is called bubble sort. I will play this GIF so you can, I'll play this GIF so you can visually understand. Bubble sort algorithm compares all the elements in the array one by one and sorts them based on their values. So bubble sort begins with the first element and compares the elements next to it, and decides whether the values are greater or smaller. It is called bubble sort because the elements quite literally bubble forward to their correct position. So if it is provided with a random array of n elements, it will need to iterate through all of the elements to sort through completely. Hence, it iterates for n minus 1 times at minimum. Now I will show you the code for bubble sort. I got this code from geeksforgeeks.org. And honestly, the bubble sort code is kind of simple. It merely has two for loops, and the outer loop just iterates through all the elements. The next loop merely checks um, the next element in the list um, and compares if the previous element is greater than the next element. And if it is, it swaps these elements if sorting in an ascending order. Now, I'll talk about merge sort. Sorry. Another algorithm that is quite commonly used is merge sort. However, I would say it is kind of a little bit more difficult to understand than bubble sort. So I'll quickly play this GIF. Basically, as you're seeing, merge sort follows the rule of conquer and divide and conquer, sorry, which allows it to sort the arrays a little bit faster. When given a sorting array, merge sort breaks the uh, given array midway. For example, as you can see, this GIF this array initially had 8 elements, then it split into um, 8 arrays actually, with 1 element each. And um, so merge sort keeps dividing the arrays until all the arrays only have 1 element. Then it compares each element in the array and organizes it simultaneously, so all the elements are in the correct order, as you can see here. It compares both elements in the array and then places the elements in correct order, kind of like a zipper. So now I'll show you the code for merge sort. So the two most important parts of this code are these two functions, the merge function and the sort function. The sort function is the main function of merge sort because it's the iterative function that checks if that firstly splits the arrays midway and then um, compares, calls the merge function and compares the elements in each array to organize it chronologically. This code is quite complicated, so you can take a look at this code for yourself more on the Geeks for Geeks website. So the next sorting algorithm we will look at is insertion sort. Insertion sort basically goes through all of the elements in an array and inserts the correct element when given. So you can look at this GIF to help you better understand. It basically creates two lists, starting with the first element, then comparing the next element. After it has compared all of these elements, instead of just swapping like bubble sort did, it merely takes the element that's next to the sorted list and checks where it fits. It does this by it by doing so, it basically loops through the whole array only once, and um, makes it very adaptive if the given list is partially sorted. So the implementation of insertion sort is here in code. It is much simpler than merge sort, as we talked about previously. It basically iterates through the entire array once and uses the first element as the key, then um, compares the elements next to it to see if it is smaller or greater, as you saw with the 6 and a 5 in the beginning. And then it puts the next element from the sorted outside of the sorted list to it the correct corresponding place inside the sorted list, which it does here, and then makes the last element the key, which is in the unsorted list. So now I will talk about our last algorithm for today, which is going to be selection sort. Selection sort works by starting from the first element and then searching for the smallest element in the array, and then replacing it with the first element. It's similar to insertion sort, however, it merely swaps the elements instead of inserting it into the correct position. After it knows that it is the minimum element in the array, it never looks at it again because it checks for the minimum element um, when checking. So it doesn't need to look at the elements over and over again. The code for insertion sort is also quite simple. It firstly iterates through all of the unsorted arrays, then remembers the min and swaps it if it finds another number in the array which is smaller than the min, and um, then um, puts that number in the sorted list to never look at it again. So that was selection sort. So finally, we need to talk about space and complexity of sorting algorithms. We use the big O notation to describe the idea of space and complexity. The big O equation is basically an equation that shows how an algorithm scales as the elements inside of it grow in size. For example, an algorithm that doesn't grow at all would be referred to as the big O of 1, which means it is a linear algorithm and no matter what, it will have the same runtime. In the case of the bubble sort algorithm, um, the algorithm has an average time complexity of big O of n squared, n being the number of elements in the array. Because a bubble sort needs to go through the elements at least n minus 1 times and more if the list is still unsorted after its first pass. So adding n minus 1, n minus 2, and n minus 3, and so on gives us n times n minus 1 over 2. After multiplying n by n, the rest of the equation becomes negligible, which is why we can basically get rid of it, and then we're left with the n squared part of the equation. Hence, 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 bubble sort takes n squared time to sort through all the elements in the array. However, its best case scenario is only big O of n, because it will only have to go through the list once, since all the elements will already be sorted. As you can see, according to the table, merge sort is the fastest algorithm, because log of n is very small, and it multiplied by n is much smaller than n squared, which all the rest of the algorithms have as an average time. However, it is the one that uses the most space because, as you might recall, it splits all the elements into single arrays. It splits all the elements until the elements are in their individual arrays, which takes a lot of space. Hence, after merge sort, however, in terms of time, the two best algorithms are bubble sort and insertion sort because they both have a big O uh, of n squared, and also their best case scenario is only big O of n, unlike selection sort, which has a big O of n squared for the best case scenario. Now, I know that the big O notation is quite confusing when you hear it the first time, so I will quickly play an illustration to help you visualize the speed of the algorithms. So this is a table with different algorithms that I can play, and the first list on this table will be a randomly sorted list. Okay, as you can see, the elements are quite random, and so the algorithms will have to sort these elements by themselves, all of them. And the next row on this table is nearly sorted elements, which means, of course, they're partially sorted, and this one is like the elements are all reversed, so it will have to reverse the elements. And finally, the last one is few unique elements, which means some of the elements are the same. So I'll play it and pay attention to these four algorithms that we learned today: insertion sort, selection, bubble, and merge sort. As you can see, merge sort won first, and selection sort came last. However, they were all different for the different four types of arrays. You can see that insertion sort actually wins with a nearly sorted array, and actually selection sort never wins with any of the arrays. It's the smallest, it's the slowest for all of the arrays. So yeah. So all right, thank you for watching. I hope you learned something. Bye.